Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 4, consists of me, Muhammad AKASHAH, Muhammad IMRAN HAZIQ, DALILI FAIQAH, and PUTRI AUNI BADRINA. Will do a presentation video for our mini projects, which is paper review with 2VEC 2.0, a framework for self-supervised learning of speech representations. As we know, speech recognition powers applications like real-time transcriptions, virtual assistants, and natural human-computer interactions. But traditional ASR systems depend heavily on large label datasets, which is expensive and time-consuming to produce. So, self-supervised learning offers a promising alternative by learning from raw and unlabeled audio. This presentation reviews Wave 2VEC 2.0, a framework by Facebook AI Research that significantly improves ASR performance with minimal label data. So this is the problem background of this paper review. Conventional ASR relies on handcrafted features, for example, MFCCs and filter banks. They also relies on large label datasets. The limitations: high cost and effort in data annotations, and infeasibility for low-resource languages. Earlier models, such as Wave 2VEX and CPC, show potential but had drawbacks, which are dependence on handcrafted features, discrete quantization limiting flexibility, and poor long-range dependency modeling. Next, these are the statement and scope of the paper. The objective of the paper is to train high-performing ASR models using self-supervised learnings and minimizing reliance on labeled data. The key insight of the paper is Wave 2VEC 2.0 achieves competitive performance even with just 10 minutes of labeled data. The scope of this review is: first, architecture designs, which is raw audio inputs, no manual alignment or quantizations. Second, pre-training, which is large-scale unlabeled datasets, such as LibriSpeech and LibriLikes. Third, fine-tuning, which is small labeled datasets used for ASR. And lastly, evaluations, where the paper do the benchmarking against supervised and self-supervised baselines.
Hello, I'm Imran and I'm gonna present and explain about WAV2VEC 2.0 model architecture. So, to start, it's made out of three core modules that work together to learn speech representation from raw audio. So first, we have the feature encoder. It's a convolutional neural network module that takes in raw waveform audio and then transforms it into lower dimensional latent representations. Think of it like extracting basic patterns from the sound signal. This forms the foundation of everything the model learns. So from there, from what they extracted from the feature encoder, it goes into the context network, which is built from using transformers blocks. Its job is to process the sequence of latent features and understand the broader context, like how words relate to each other over time in a sentence. This helps the model capture long-range dependencies in speech, by understanding the context of the audio. So thirdly, we have the quantization model. It discretizes the continuous latent features using product quantization and the method called Gumbel softmax. This turns the feature into a finite set of code book entries, which are then used for contrastive learning tasks. This is crucial for training the model in a self-supervised way without needing label data. So together, these three models allow Wolf2Vec 2.0 to learn high-quality speech representations from raw audio, even with very little label data. Now, that's the model architecture covered. We move into the pre-training phase, which is where we set up where it set up the model to learn representations from raw audio. First, the model performs mask latent prediction. It masks random portions of the latent features and tries to identify the correct quantized vector from a pool of negative examples. This encourages the model to understand and learn useful speech patterns. So, in order to to find guidance for this learning, WAF2VEC 2.0 uses two key losses, which are contrastive loss and diversity loss. The first the loss, and these losses are summed up into the total function loss, as you can see the equation. So contrastive loss is it pushes the model to bring what used for is to push the model to bring the correct target vector closer to the mask representation while pushing away distractors. It uses constant similarity to compare. Then diversity loss, it ensures the model doesn't overuse just a few codebook entries. It increases the entropy of the selections to promote variety. So, thirdly, to make this possible, the model uses quantization with Gumbel softmax. It's a technique that allows it to choose discrete vectors from codebooks in a way that is still trainable through backpropagation. And then these quantized vectors act as targets during training. Then together from these three, these techniques allow the model to learn meaningful speech representations from unlabeled audio. Now we go into the fine-tuning phase. At this stage, we add a simple linear classifier on top of the transformer. This layer maps the model's output to tokens for task-like speech recognition. And this model is trained using connectionist temporal classification or CTC loss, which allows it to predict sequences without needing precise alignment between audio and text. And to improve performance and avoid overfitting, especially with limited label data, the model applies spec augment, a data augmentation method that randomly masks timestamps and channels in the feature space during training. So, have techniques like L2 regularization and gradient scaling is used to further stabilize training and help the model generalize better. Together, these techniques make the model highly effective even in low resource scenarios. And in to the right, you see the table summarizing all the components of the model and each algorithm it includes with the studies reference in each. We have back feature extraction, we have CNC coder, context modeling with the transformer, discretization, product quantization plus global softmax, the learning objective, use, to find the sum of contrastive loss and diversity loss. Lastly, the supervised fine tuning using CTC loss plus spec augment. As you can see, the respective studies. And that's all for me. Let's go to the next part of this presentation.
Next, we will discuss about the results and discussion that we get from the paper. There is three tables, which is the low resource setting, high resource results, and the ablation study. So for the first table, which is the low resource setting, we can see here that the table shows the the REF2 VEC 2.0 performance with very little labeled data. Even with just 10 minutes, it achieved 4.8% WER on test clean and 8.2% on test other. As labeled data increased to 100 hours, WER drops to 2.0% and 4.0%. This demonstrates that self-supervised pre-training on massive unlabeled audio enables strong recognition even in low resource settings. On the second table, which is the high resource result, we can see the result with the full 960 hours of labeled data. The large model pre-trained on 60,000 hours of unlabeled data achieved the best WER at 1.8% and 3.3%. This shows that scaling both model size and unlabeled data improves the accuracy even in the high resource setups. And in the third table, which is the ablation study, the table analyzed the architectural choices. The best results come from using the continuous inputs with quantized targets, achieving 7.97% WER. Quantizing inputs harms performance, showing the importance of perceiving rich representation in the model design. Overall, the REF2VEC 2.0 shows strong results in both low and high resource settings thanks to the effective self-supervised pre-training and well-chosen architecture.
Assalamualaikum and hi, my name is DALILI. I will be continuing with the paper shortcoming suggestion for improvement, and my friend Putri will continue with the work demo, and I will conclude this overall mini project. So for paper shortcomings, although Wave 2 VEC 2.0 achieved the state-of-the-art performance, it comes with several limitations. Firstly, it requires massive computational resources, up to 128 GPUs, just for pre-training. This makes it inaccessible for researchers or developers who lack such infrastructure. It also relies on large amounts of unlabeled audio, such as the 53,000 hours of LibriVox. This might not be realistic for low-resource languages that don't have access to such data. In terms of output, the model still uses character-level tokens, which could limit its performance in morphologically rich languages. Lastly, although the results of LibriSpeech and Timid are strong, the model hasn't been tested much in real-world noisy environments or spontaneous speech, which raises questions about its generalizability. To address these issues, a few improvements can be considered. Switching from character level to word piece units can help the model better understand the structure of language. Also, integrating a sequence-to-sequence decoder instead of just using CTC might lead to more coherent predictions. Reducing model size with distillation could make it more accessible for smaller setups. We also suggest training and releasing models on more realistic speech datasets, including noisy, conversational, or domain-specific audio. Lastly, combining this approach with techniques like pseudo-labeling or domain adaptation could help improve performance without requiring so much data.
Okay, so on this slide, I'm showing the working demo of our mini project using the FAIQAH library, which is written in the paper. So FAIQAH is an open source toolkit for sequence modeling built on Python. So we use it to train a toy English-French translation model from scratch. So you can see there will be three screenshots, which is the pre-processing, training, and the interactive translation. So for this first slide is the pre-processing, where we use the FAIRSEC pre-process to tokenize and binarize our parallel English-French data. The terminal output here shows the dictionary built for both language and that the data was prepared for the training. On the second slide here is the training, which we train with the FAIRSEC train using a transformer architecture. You can see here the log shows multiple epoch, which is you can see is which is epoch 1 and epoch 2, and then the training loss, validation loss, and the perplexity. We can also see the automatic checkpoint training. In here, we train using maximum 10 epoch. On the final slide here is the interactive translation, where we tested the train model with the FAIRSEC interaction, where we entered the English sentence, which is, as you can see here, hello, I am tired, and be quiet, and got the model French translation. However, since our training data was very small and simple, the results are very limited and incorrect. As you can see here, it only shows J, which is obviously incorrect. This is because of the limited training data.
In conclusion, Wave2Vec 2.0 is a powerful step forward in speech recognition. It proves that self-supervised learning can reduce the need for expensive labeled datasets. By masking latent representations and learning to predict quantized targets, it creates rich speech embeddings that generalize well. With a few targeted improvements, especially around accessibility and real-world deployment, Wave2Vec 2.0 could truly become the backbone of multilingual, low-resource speech technology in the future. That is all from Group 4 Mini Project. Thank you.